In this video, we are going to learn the concept of table functions in ProModel. First, let's see what do we mean by table functions. So here I have a simple function, y equals to 2 multiplied by x plus log of x. So in this function, you define what is the value of the x, and then given this closed form expression, this function can tell you what is going to be the value of y. So here x is what we call as independent variable. You can decide on the value of x independently. And then y is what we call as dependent variable, because the value of the y depends on the value of the x. Okay. So this is the scenario where we have a closed form expression between dependent variable and independent variables. However, if that's not the case, such as this table, so in this table, I have the time of the day at hour 2, at hour 3, at hour 4. And then here in this other column, I have the interarrival time of customers as an example. Interarrival time of customers to a store, let's say. So still the time is the independent variable. It's the time of the day. Is something that we have to specify. We have to decide on the value of the independent variable. And then using this table, I can tell you, given the time that you're going to give me, I can tell you what is going to be the interarrival time of the customers at that time. Okay, so still this table has a column for the value of the independent variable and has a column for the value of the dependent variable. Depending on the value of the independent variable that you pick, we are going to know the value of the dependent variable, which in this example is interarrival time of customers to the store. So this is what we call as a table function. It's still performing the role of a function, but as opposed to a closed form expression like the one we have here on the top, what we have here is a table. Still, you have to decide the value of the independent variable, and this table function is going to give you the value of the dependent variable. So we can define table functions in ProModel, and they're going to enable us to capture a lot more complexity in the model. So let's go through one example and see how table functions can help us to capture some characteristics that otherwise we wouldn't be able to do. So this is the example that we want to go through. So customers come to the incoming, then they do their shopping in aisle 1 and 2. And then from there, they go to the cashier queue and then to the cashier to pay for the items they have picked and then leave the system. So now let's look at a couple of details related to the model. 70% of the customers that come to the system will get some items from aisle 1. 50% of the customers that come to the system will get something from aisle 2. Customers in the system can buy something from aisle 1 or aisle 2 or both of them or none of them. System has to give this possibility. The number of items that the customers pick from each aisle has uniform distribution between 5 to 15. The time to pick up each item from each one of these aisles has normal distribution, average 5, standard deviation 1. And the time to pay for each one of these items and the checkout has uniform distribution, average 1, and half width 0.3. There's one more piece of information that we have here, which I have specified in this table. So the interarrival time of the customers to this grocery store is not like one number for the whole day. So it's not that I can tell you the customers arrive with interarrival time of, let's say, 30 minutes, exponentially distributed for the whole simulation time. This is not the case here. The interarrival time of the customers that come to the system has exponential distribution, so it is random. However, that average of that exponential variable is not fixed throughout the whole simulation time. It's going to change in different times of the day, which is very reasonable for a grocery store. So between 8 to 10 a.m., interarrival time of the customers is 50 minutes, exponentially distributed. Between 10 to noon is 40 minutes. Between 12 noon to 2 p.m. is 25 minutes, and all the way to the last hours of working of this store in a day, which is 10 p.m. to midnight, which is 30 customer per hour, which is 30 minutes. And again, all of these interarrival times are exponentially distributed, and they are in minutes. So as you can see, if I want to model this grocery store for the whole day, I don't have just one average for interarrival time exponentially distributed that I have to use for the whole simulation time. The interarrival time changes as throughout the day or as simulation time passes. So we want to see how we can capture this table in ProModel. And that's where the table function feature is going to help us. So here, if I want to look at this table, obviously time is my independent variable, and the interarrival time, or the time between intervals, is my dependent variable, right? And here, 8 a.m. to 10 a.m. in simulation time is going to be 0 to 2. 10 to 12 is going to be 2 to 4. 12 to 2 is going to be 4 to 6. And we can do all these calculations all the way to the very last one, which is 14 to 16. Okay, so these hours I wrote here, they are basically simulation time. The hours that you see on the left are the hours in the real world. The ones that you see here a little toward the right, they are the simulation times. Okay, so in these simulation times, I want the interarrival times to vary, and these are the value of the interarrival times. Okay, so what I need to do is to create a table function in ProModel in which my independent variable time is going to be defined, and then the value of the dependent variable, which is going to be interarrival time, is going to be defined as well. So then later, when I use the when I'm going to define the arrival of the customers to the system, I need to use this table function to find out what is the frequency at different times of the simulation. Okay, so we are going to do that. So I want you guys to please create a model, name the model as grocery store table functions, grocery stores dash table functions. And in this model, these are the locations we are going to have. Incoming, L1, L2, cashier, queue, and cashier. For all the queues, consider capacity of infinity. The queuing rule is first in, first out, and make sure all of them are queue. And you can consider the length of these queues to be 20 feet, just for our numbers to be similar. And for the incoming and cashier, consider the capacity of 1. Okay. And our entity is going to be customer. And for the arrival, customers are going to go to the incoming one at a time from the start of the simulation for as long as I run the simulation. However, for the frequency, I cannot just simply say E30, for example. That means for as long as I run the simulation, interarrival time of customers is going to be 30 minutes exponentially distributed. That's not the case. We just saw in that table that interarrival time of the customers is going to change in different hours of the day. So we want to be able to capture that. So we cannot write it this way. So I need to define a table function. To be able to do that, first I go to the analysis menu. And here we can go to the table function option to define table functions. So here I can define the name of the table function. So I'm going to call it arrival table functions, TF. Okay. Now I have to define the table. So just double click on the table, and then this tab here opens, which is going to help enable us to define the table function. We can identify the value of the independent variables and then the value of the dependent variables. Okay, so this is how we are going to define the table function. Now let's go back to the original table and see and look at the structure one more time. So here, from time 0 to 2 in the simulation, interarrival time is 50 minutes. And then from 2 to 4, interarrival time is 40 minutes. Okay. So how we are going to define this in a table function? So from the independent variable, that's our time. Okay, so from time 0, we are going to start an interarrival time, which is the value of our dependent variable, is going to be 50. Next, press enter. This is going to continue till time 2. At time 2, the interarrival time is going to change to 40. And that's going to continue till time 4. Okay, so the way that ProModel is going to interpret these 3 rows is that from time 2, from time 0 to 2, interarrival time is going to be 50. And then from time 2 to 4, interarrival time is going to be 40. And we are going to use the same logic to define the values for the table of the table function for other times of the day as well. So from time 4 to 6, interarrival time is 25, and from 6 to 8 is 20. So from 4 to 6 is going to be start with 25, and it goes all the way to 6. And at 6 is going to change to 20 again. The way simulation is going to read this, from 4 to 6 is going to be 25, and at 6 is going to change to 20. And that's going to continue for another 2 hours till 8. And then at 8 is again 20 as well. And that's going to change, continue for another 2 hours to up to 10. And yet up to that point is still 20 minutes for interarrival time. So as you can see here, so from 8 to 10 is 20 minutes, and then it's going to, for the next 2 hours, 10 to 12, it's going to continue to be 20 minutes. And then from 12 to 14, it's going to be 25 minutes. And then from hour 14 to 16 in the simulation is going to be 30 minutes. So starting at 10, it's 20 minutes, and it's going to continue 20 minutes for another 2 hours. Okay. So it's going to continue till hour 12 for another 20 minutes. And then at hour 12, it's going to change to 25, and it's going to be like that for another 20 minutes till hour 14, where it's going to change to 30. And that's going to be the case up to hour 16. So from hour 14 to 16 is going to be 30. Okay, so what I need to do here to be able to close this table function, I have to specify for how long this the interarrival 30 would last. So it will last for another 2 hours till hour 16, and at hour 16 it's just 30 minutes. It's whatever it has been for the past 2 hours. Okay, so I just put the last hour. At hour 16 is still 30 minutes. It's going to continue to be 30 minutes. Just so I close the whole time interval in this table function. We started from 0 and we closed at hour 16. Okay. So now I have the value of all the independent variables and the value of all the dependent variables in this table. So now that we have defined the table function, we're going to go back to the model. Let's go back to home, click on the arrivals. Now I want to use the value of that table function to identify the frequency or interarrival time of customers to this system. So interarrival time, as you have seen in the table and the problem statement, it has exponential distribution, E, okay? However, the value of the interarrival time, which is the value of the dependent variable, is coming from that table function. The name of the table function was arrival underline TF. And in this table function, to be able to get the value of interarrival time, which is my dependent variable, first I have to pass the value of independent variable to the table function. And our independent variable is simulation time. Okay, so I have to get the simulation time as an independent variable, pass it to this table function, and this table function is going to return the value of the dependent variable, which is interarrival time. So the value of the independent variable, which is simulation time, can be called by using the function clock. Okay, and then I need the simulation time in hour. just because in my table function, I have defined the times in hour. Okay, so by clock hour, I can get the value of the independent variable, which is simulation time. I'm going to pass it to this table function. Okay, and this table function is going to return the value of the dependent variable, which is interarrival time, corresponding to that hour in the simulation. So that will conclude how I'm going to define the frequency using that table function. And that table function will allow the frequency or interarrival time of the customers to change during the simulation time. As simulation hours pass, there is a possibility for these interarrival times to change, and we could capture that using the table function feature. Make sure to save, guys, as we proceed. Now let's go to the processing. Just to refresh your mind, what I have here in the processing is that 70% of our customers go to aisle 1, and 50% also of all the customers can end up also buying something from aisle 2. Just I want you guys to pay attention. These probabilities are not complement of each other. I'm not saying that of every customer that comes to the system, 70% of them go to aisle 1 and only aisle 1, and then 30% of them go to aisle 2 and only aisle 2. That's not the case. What I'm saying here is that of all the customers that come to the system, we have done an analysis. 70% of them end up buying something from aisle 1, and 50% of all the customers that come to the system also end up buying something from aisle 2. So some of the customers that end up in aisle 2, for example, may have bought something from aisle 1 as well, and some of them may not have bought something from aisle 1, and vice versa. So first we have to capture this part. So what I'm going to do is that I'm going to create a new virtual location. And I'm going to tell you in a little why I'm going to create this additional virtual location to be able to, so that I can capture that probability things. So let's go back to the location. I'm going to just define a new location here. I'm going to put it here. And I'm going to call it as, and I'm going to keep it as capacity of 1. Now let's go back to, so our customers that are initially at incoming, 70% of them is going to go to aisle 1. And this is going to happen with probability of 0.7. And okay, I'm going to send the other 30% to this little virtual location that I created. So the other 30% are going to go to the check location. Okay. So what happened here? Of all the customers that came to the system, I know 70% of them end up buying from aisle 1. I keep the other 30% here. Let's go to aisle 1. So the customers go to aisle 1. They do their shopping. And I'm going to write down in a little bit how we are going to capture the processing time at aisle 1, the wait time at aisle 1. Bear with me for a second. So we're going to do that. So after they're done the shopping at aisle 1, then they are going to go to the check location, this new virtual location I created. So what does this tell us? It tells us of all the customers that came to the system, 70% of them buy something from aisle 1. I keep the other 30% here at check. And that 70% also, when they are done at aisle 1, they also are going to end up at check. So now at the check location, for one more time in the simulation, I have every customer here. Okay, so of all the customers are at the check location. Again, I can follow the same logic and say, okay, now that all the customers are at the check location, of all those customers, I know 50% of them end up buying at aisle 2, and the other 50% have already either bought something from aisle 1 or not, but no matter what, I'm going to send them to cashier queue. So of all the customers that are at check, again, these are all the customers at this point. I want to make sure that I allow for 50% of the customers to go buy something from aisle 2, and the other 50% are the ones that are either have bought something from aisle 1 or not, but no matter what, I'm going to just send them to cashier queue so that they can pay for their items. Okay. And then now, of all the customers that ended up in aisle 2, they bought their items again, and we are going to calculate the waiting times in aisle 2 in a minute. But after they're done with shopping at aisle 2, then these customers also continue going to the cashier queue so that they pay for their items. Okay. So this technique enabled us to capture this feature of this model, which we did not have before, that to allow of all the customers to this that come to the system, 70% of them go to aisle 1 for shopping, and of all the customers that come to the system, allow 50% of them to buy something at aisle 2. Okay, so and this would enable the customers in the systems for the entities to buy something either from aisle 1 or aisle 2 or both of them or none of them. And then after that, no matter what, we send them to the cashier queue and then to the cashier for the payment. Okay. And now here also, let me just add that when the customers end up to at cashier queue, then they go to the cashier and from the cashier to exit. Let's go back and calculate the processing times in aisle 1, aisle 2, and the cashier queue. As you can see here, the number of items that the customers pick from aisle 1 or aisle 2 has uniform distribution between 5 to 15. And this is the time for picking each one of those items in each one of the aisles. That has normal distribution, average 5, standard deviation of 5. So when I know number of items that they pick at each aisle, then I have to multiply it by this number so that I can find the total time it takes to pick the items from each one of the aisles. And then when they get to the cashier queue, when they get to the cashier, I have to know the total number of items that they have picked so I can multiply that by this number, because that's the time for the checkout of every single item. So if I want to know the total checkout time, then I have to multiply the total items that they have picked by this times to find the total checkout time. So if that's the case, then as they go to aisle 1 or as they go to aisle 2, I have to keep track of the number of items they have picked so that when they get to the cashier, I know the total items they have picked, the sum of the items they have picked in aisle 1 and aisle 2. To be able to do that, there are different ways to do it. But one way is to define an attribute. And that in that attribute for each entity, I'm going to save the total number of items they have picked in aisle 1 and aisle 2. Okay, so I'm going to define an attribute. I'm going to call this item. I'm going to call this attribute as item. It's going to be integer. That is going to hold the number of items they have picked in aisle 1 and aisle 2. Okay. Now, in aisle 1, what happens to the customers when they get to the aisle 1? First, I need to know how many items they are going to pick. And then, given the time that it takes to pick each item, I find the total wait time in aisle 1. I'm going to save the number of items that they are going to pick in aisle 1 in a local variable. And I will tell you in a minute why. So here I'm going to define a local variable. That local variable is going to be integer. I'm going to call it as item1. In this local variable, I'm going to save a random variable that has uniform distribution between 5 and 15, which is average 10 and half width 5. That would be the number of items they pick from aisle 1. And for the wait time, that's going to be the number of items they have picked from aisle 1, which is now saved in this local variable item1. And now that I know the number of items that they have picked, I'm going to multiply that by the normal variable that has average 5 and standard deviation 1. And that's the time it takes to pick each one of the items. So the number of items multiplied by the value of this normal variable is going to tell me the total waiting time in this aisle. Okay. And next, also, and remember, this local variable is also it's only known here, right? However, if you remember, I told you we want to define an attribute, and in this attribute for each entity, we want to calculate. We want to save the total number of items that the entity has picked from aisle 1 and aisle 2, so that when it gets to the cashier queue, we know how many items that entity has picked or that customer has picked in total. So what I'm going to do here is that in the attribute item that we created, I'm going to save the value of this local variable. So whatever number of items this customer ended up picking in aisle 1, which I already have saved in item 1, I'm going to save it in the value of this attribute item, which is for that specific customer. The reason is that when the next customer comes, I'm going to rewrite the value of item 1 depending on the number of items that the second customer is going to pick. Okay, so the value of item 1, the variable item 1 is going to change when the second customer comes and the third customer comes and fourth customers and so forth. The value of this local variable is going to change. That's why right away, right here, I'm going to save the value of this local variable for this specific customer at the attribute item so that I can save it there. And that attribute is just for that specific entity. And so I have saved the number of items that the customer picks from aisle 1 in that specific attribute. So I'm going to do a similar thing for aisle 2. So I'm going to define a local variable. I'm going to call it, that local variable is integer. I'm going to call it item2. In item 2, I'm going to save the number of items that the customer is going to pick from aisle 2, which is average 10, half width 5. And then the waiting time in that aisle is going to be item 2 multiplied by normal 5, 1. And lastly, now so far I know what is the waiting time in aisle 2. Okay, good. However, I also want to make sure that in that attribute item, which already knows the number of items that we have picked from aisle 1, I also want to add the number of items that we picked from aisle 2. To be able to do that, I say item equals to item plus item 2. Okay, so with this, I already have the value of the attribute which has everything from aisle 1, and I'm going to add the number of items that we pick from aisle 2 to it, and I'm going to save it in the same attribute. So by this point, the value of the attribute item has the total number of items that the customer picked from aisle 1 and aisle 2. Then when I get to the cashier, I have the total number of items that the customer has picked, and that's the one that has been saved in the attribute item. And I'm just going to multiply that by the number of by the time that it takes to check out or pay for each one of those single items, which is uniform distribution, average 1, and half width 3. So that will take care of the processing time at the cashier. And then after that, the customer leaves to the exit. Okay. Make sure to save it before we proceed further. And then we are going to run the simulation at this point only for 16 hours. So here is the result. About 43 customers got the service and left the grocery store in 16 hours. And they spent about 72 minutes in the system. Let's go back to the model and let's try to run the system for, let's say, 24 hours. So you see, as soon as we got to hours 16, as soon as we are going to pass hours 16, we got an error. And this error says that in the arrival TF, the arrival table function, we do not have any interarrival time, any value identified for the dependent variable, which is the interarrival time, past hours 16. So that's why we get an error. As soon as the simulation time passes 16, we get an error. So as I mentioned, that's the reason. In table function past, we don't have anything after hours 16. So as soon as the simulation goes to hours 17, 18, and so forth, then the table function is not going to return anything because those values for time are not listed in the table. So no value is going to be identified for the interarrival time. So the simulation then gets an error. So what we need to do is to go back to the arrival and somewhat try to make some adjustments here so that after we pass hour 16, we still can continue running the simulation. So one thing we can do here is that if I just want to continue running the simulation, let's say I want to consider the first 16 hours as the first day. I want to consider the second 16 hours of the simulation as the second day, the third 16 hours of the simulation as the third day, and so forth. I can potentially write the time as a clock in our mode 16. Okay, so when I pass the time to table function, instead of just simply passing clock, if I pass clock mode 16, then obviously for the first 16 hours, numbers like 1, 2, all the way to 16 are going to be passed to the table function, which is good. We have corresponding interarrival times in the table function. But when the simulation goes to, when the simulation passes hour 16, then this function clock mode 16 still is going to return numbers in the order of 1, 2, 4, 5, all the way to 16. So, and then when we get to the third 16 hours of the simulation, again, clock mode 16 is going to return numbers in the order of 1, 2, all the way to 16. So then we are not going to get any error when we run the simulation and when we pass hour 16. However, I want you guys to be mindful that the way that I'm changing this right now, clock mode 16, basically says that I'm going to consider the first 16 hours as the first day, the second 16 hours of the simulation is going to be the second day, the third 16 hours of the simulation is going to be the third day, and so forth. Now, if I want to run the simulation again, I'm going to run it for 160 hours, let's say. Run. And as you can see here, the simulation ran without generating any error, just because we were somehow able to address the issue related to table function. So that 160 hours, given the fact that each day is 16 hours, then 160 hours is like equivalent to 10 days. So as a result of working for 10 days in this grocery store, about 400 customers got the service, and the time that I have spent in the system is 1.3 hour. So that's basically what table function is and how we can use them to capture more complexity in our simulation model.